This observatory listens for ripples in the actual fabric of the universe.
We're an hour outside New Orleans at the center of a revolution happening in astronomy. This road leads to LIGO.
In 2017, scientists here, and at their sister observatory in Washington State, won the Nobel Prize in Physics for proving one of Einstein's last unverified predictions about the universe. But their work is just getting started. For thousands of years, most astronomers have studied the small fraction of the universe that gives off light or other radiation. These scientists are among thousands finding ways to see things conventional telescopes can't. The tools they're building can help us make observations without light. And they could one day help us understand the 95% of the universe that's completely invisible.
From a swamp near LIGO, I'm Michael Tabb.
This is Quartz. Please subscribe to our channel.
When we actually saw light down at the ends, and we were dumbfounded it was there. We were like, oh my God, it actually works.
Janine Romy leads the detector engineering group at LIGO. The work is so cutting edge, it's hard to explain.
Every single time I tried to explain what I did, most of the time I just gave up. I just say it's an astronomical observatory that's something like a telescope. It's just easier that way.
But to understand why the work at LIGO is so revolutionary, we've got to try to explain what she does.
Can you see it? It's crazy robust for being as small as it is.
It all starts with Einstein. He devised his theory of general relativity in 1915, and basically no one understood what he was talking about. He described the close relationship between space and time, a relationship so close we combine them into one word. Space-time is the so-called fabric of the universe, and like a fabric, it bends under stress. That bending creates what we call gravity. Anything with mass, from a paperclip to a black hole, bends space-time. The more mass, the more it bends. Now, what happens to the fabric of space-time when those objects speed up or change direction? They create ripples disturbing space-time.
Like ripples are boats creating on the surface of the swamp.
And if you're talking about really big things, like a star exploding or two galaxies colliding, they create ripples big enough that we can actually detect them. The ripples are called gravitational waves, and these waves offer incredibly valuable insight into how our universe works. Gravitational wave observatories can show us lots of things that telescopes can't. They offer a chance to study the biggest events in our universe's history, and could explain everything from how we got here to whether our best theories of physics are actually correct. Because as much as conventional telescopes can show us, from other galaxies to starlight bending around black holes, which is really, really cool, they can't show us the dark parts of the universe. Gravitational waves, on the other hand, can show us everything. The only issue is that they're incredibly hard to detect. They're hard to even understand.
What really blows my mind about gravitational waves is that it's the fabric of space-time itself that's moving. And that's a really amazing, but also a little bit of an uncomfortable thing to be thinking about. These shifts are imperceptible to human beings, but they're happening all the time.
Until now, no instrument has ever been capable of measuring gravitational waves. In fact, Einstein thought it was impossible. But that's exactly what LIGO does.
Now let's just hope that the battery of this hold us all the way till we get back. Beautiful drive though, isn't it?
Here's how LIGO monitors for ripples in space-time. A gravitational wave squeezes and stretches space-time in a specific way. So when one passes through this observatory, one leg gets shorter while the other gets longer. The change in length is really small, 10,000 times smaller than the nucleus of a hydrogen atom. But this is one of the most precise instruments on Earth.
And you have to looking through that. Does he need a beard now or not?
LIGO made history in 2015 when it detected two black holes merging, more than 1 billion light years away.
The very first one was seen by someone, I think, in Europe, right? Because it was like 4 a.m., so that's who was awake. And basically, there's a computer scanning the data, essentially, right? And he goes, oh, this is a possible gravitational wave. But then you have this human set of eyes to look at it.
Since 2015, LIGO's detected several black hole collisions, as well as one collision between superdense objects called neutron stars. But LIGO can only detect some gravitational waves. It's only able to hear very specific frequencies. Other researchers are looking to study the gravitational waves that LIGO can't hear, whether it's because they never pass through the detector or because the frequencies are too low.
There wasn't always light in the universe. If you want to study things that happened immediately after the Big Bang, there was no light at that time, but at the time we still did have gravity. And it's possible to even detect gravitational waves from the Big Bang with these gravitational wave experiments.
Chiara Mingarelli is an astrophysicist and member of NanoGrav, a consortium of scientists from around the US. Along with their peers from Europe and Australia, they're using a network of radio telescopes to effectively create a gravitational wave detector the size of our galaxy.
That's so cool. It's slippery.
This is Green Bank Telescope. It captures radio waves from space. And it's a pretty important local landmark because if you're anywhere near it, you can't use your cell phone since it could screw up the observations. For the past decade, researchers have been using the telescope to observe spinning stars known as pulsars that release bursts of radio waves. These signals arrive with amazing consistency. When a gravitational wave ripples through Earth, it squeezes and stretches space-time, making some signals arrive faster than expected, and delaying others. Gravitational wave researchers have been timing dozens of pulsars across our galaxy since 2004, and looking for patterns that show gravitational waves are passing through.
A lot of light can obscure what's going on in the center of a galaxy, but gravitational waves, if you have a supermassive black hole merging with another one at the center of a galaxy, those gravitational waves don't care if there's stars in the way or gas or dust because it's the fabric of space-time itself that's moving.
That means detecting gravitational waves is sort of like seeing in the dark. LIGO listens primarily for black holes around 10 times the mass of our sun crashing into each other, which create waves that pass through us incredibly quickly. Astronomers looking at pulsars are searching for something very different.
So, when we first start to see it, it probably won't even be very visible to the eye.
They're trying to hear the sum of all the gravitational waves over the history of the universe. They call it the gravitational wave background. They're also listening for supermassive black holes at the center of galaxies crashing into each other. These waves might take years to pass by, meaning it could take decades of data to be sure we've detected them.
So when we first started, about 10 years ago, it seemed like kind of a pipe dream, like it was a good idea, it was fun, but it seemed like kind of way out there, And now it feels like we're on the brink of just an entirely new field of astronomy and physics, and it's just so exciting to be part of that.
These experiments are just the beginning. More countries are building detectors like LIGO to join in an international effort to locate black hole or neutron star collisions in the sky. The European Space Agency is also planning to launch an observatory into space in 2034. It should work similarly to LIGO, but with mirrors separated by millions of kilometers. By eliminating background noise, it should be more precise than any gravitational wave observatory could be on Earth. Now that we've detected gravitational waves, the question isn't whether they exist, but what they can teach us about outer space. Observing them is like adding sound to a movie that's always been silent. They're a way to observe the invisible phenomena that shape the cosmos, complementing what we can see to help us finally understand the universe.
I think, oh my God, what if it gets to a point where it's not special effects and we actually can see black holes actually colliding? What happens if we actually get to see two neutron stars going in spiral and actually exploding? Wouldn't that be, what if we get to see a supernova? Because really, that's like, that's the gold standard for us. These are like things that we could actually be like in our future.
Hey, we're making a series for Quartz members we think you'll like. It's called Exceptional Humans, and it's about people whose minds stretch the limits of human potential. Click here to sign up for a free membership trial to get full access to exclusive videos and articles. Quartz members get a daily education on the forces reshaping the global economy.